Good afternoon. It's just about 12 noon here. We're going to get into this Yaesu FT1000 let's see, it's a FT1000MP MkV. Does it have enough names? I figured I'd try this wide view of the shack here. And let's see, what's news to report? Art Bell died last night. He will be missed. If you're a ham radio operator, or know a few ham radio operators, or have any interest in the history of radio, you'll know names like Art Bell and Gene Shepard and those kinds of guys. The interesting pioneers of late 20th century radio. Anyway, he will be missed. Well, I missed him already when he retired from the show. I thought it went all downhill from there, but that's neither here nor there. A couple of things from last video, working on the TS440. I mentioned static guard. I did find it. Here it is. Let me put it here. Here it is. Static guard. I presume it's still on the market. This is an old can. But still got some in there. And what did I say it was? Some ammonium something or other? Can be, oh, ammonium, a ditallow. There we go. It's a dimethyl ditallow ammonium chloride. And, oh yeah, and I made a mistake in the video last time also. I mentioned going around looking at electronic circuits and determining if biases are right and transistors are functional and stuff like that. And I said common collector. I meant to say common emitter. By the way, speaking of common emitters and the like, I have a channel to recommend, W2 AEW, I believe. Radio, Physics, and Electronics. Excellent YouTube channel. I believe his name is Richard. Does tutorials on basic electronics. He doesn't mince words. He gets into the math. He gets into the weeds. And he's thorough and concise and clear and just excellent. I recommend him highly for those of you who want to learn more about basic electronics and its applications in radio. Okay, let's move on here. As always, we've got this. I'm sparing you the painful bits of taking all the screws out of this radio, which really wasn't that bad because half the screws are missing anyway. Not uncommon. Another case of I tried to fix it and couldn't, so now I have to pay somebody. So here we are. Now, I don't want you to think that I'm setting you up or I'm faking it or doing things ahead of time. But you know, in the last video I said, remember, 95% of all the problems are going to be connections. And lo and behold, we open the radio up, and what do we find? All the problems are basically connections. But it was a good example, and I had no idea that was going to happen that way. Well, here we're going to be going into some great depth into deciphering or decoding the service manual. And in prepping for this, and I did prep for this, which is something I rarely do, but my videos are getting to the point where I really have to start prepping and scripting. So in prepping for this, I discovered that the manual contains quite a few of, not mistakes, but ambiguities. Things left out, and we're going to be going over all of that. We're going to be doing some reverse engineering of the schematic, looking at things, determining and finding out things that the manual does not have that are important, and just methods of working that are not in the service procedure. The service procedure doesn't tell you why you do anything. And sometimes that's really nice to know. Anyway, we'll be going through all of that. So for now, let's start with a good visual inspection of the radio. What we have is this FT1000, which is a 200 watt transceiver, which is quite a bit of wattage. And interestingly enough, this transceiver has both a class AB, which is characteristics of a push-pull. I never remember which is push and which is pull. That's a joke, in case you didn't know. Anyway, it's a push-pull. In this case, FET-driven transformer coupled broadband transformer coupled amplifier capable of 200 watts. And it has both a class AB and a class A output. Now, how much up the load line is it? Is it truly class A, or is it just, you know, AB with a lot more A than B? I don't know. We'll find out when I read the manual and it tells us what to set the drain currents to. And that's what we're going to do. So we suspect that the problem with this amplifier is that one or more of these drivers has failed. Well, here's the driver, and here are the finals. And you'll notice over yonder there is a hole with no part. And we're gonna talk about that quite a bit, actually, because it's very interesting why there is no part there. And whoops, sorry, hit the camera. It's very interesting why there's no part there, and why perhaps there should be a part there. I also noticed that there's no capacitor there, and that kind of surprises me. But again, we'll discuss all of that shortly. This is the input. RF input comes in at this end of the board. There's a little coaxial connector here, which we're going to move out of our way, and a couple of plugs. I'm also going to disconnect power. This radio uses high voltage on the finals, which means the less current needs to be carried by the board, which is always a good thing. And the impedance between the drain and the final output is going to be a little closer together. The transformation ratio of this output transformer need not be as high as on a radio designed to operate in a vehicle, such as the 440 we just finished up. So that means fewer turns, lower operating flux levels, magnetic levels, and just a happier overall situation. It also gives you a little bit more load line to work with, since the solid state stuff they're all basically current devices. Their linearity improves as the voltage across them gets greater generally. Okay, so we got some of that. Now we've got a couple of small plugs that we're also going to get out of our way. Now I am going to get this entire radio off my bench. Here we are. Is that enough buttons and knobs for you? It is for me. So we're going to put this down, presumably someplace safe. Okay, I'm going to turn that background noise off, and let's move the cameras around a little bit. Now, you may or may not have noticed, I am not wearing my wrist strap. Should I be? Yes, probably should. Am I going to? Probably not. So, first thing we're going to do is we're going to open these devices up. If that's not feasible, we're going to at least open the drains, because what we intend to do here at some point is we want to look at the bias voltages on the devices and make sure that all of our bias circuitry is working properly, that we're able to sweep between, well, basically some voltage below VGS on to above VGS on, and we want to be able to sweep in that range that turns the device on and off near its, or just above its cutoff, and appears stable and properly regulated. If we can't achieve that, then there's no point in putting new finals in, because we'll just blow them up quite quickly. So we're going to do that first, and I'm going to turn my soldering iron off because I need to replace the tip. Now, I told you we'd talk a little bit about tools as needed, so now it's time to talk about soldering irons. If you expect to be doing a regular amount of surface work, one of the things that you'll absolutely require is a decent soldering iron. Any good commercial iron is certainly worth having. The Heiko, Weller, I don't know, there's a million of them out there. But you want a temperature controlled iron. And there's quite a bit of variability in terms of what is temperature controlled. I happen to use, only because I've had it forever, not that I wouldn't love to have a more sophisticated one, but this works just fine. I have a Weller WCT PN. It's a very simple iron. It's a 3-wire iron. I believe 2 for heat. No, maybe it's 4 wire. No, it's 3 wires. 2 for heat, 1 for thermostat. And the way the thermostat works on these is very interesting. It's 24 volts, little transformer and a base, little switch, and the tips have a magnet in them. And the magnets are so configured that at a preset temperature they reach their Curie point. Now the Curie point is the point at which ferromagnetic materials lose their ferromagnetic property. They no longer they are no longer paramagnetic. And the way Weller did this is they have a series of tips. They may not lose the magnetic properties entirely, but it weakens to the point where a magnet inside of here disconnects, drops out, pulls away. A spring-loaded magnet pulls away from the tip, opening a switch, which turns the heat off from the base unit. Tip cools, magnetism returns, the magnet pulls in, and anyway, on the back, on the rear, oh, there we go. On the rear, there's a number. This is number 8 on this one. Some of them say 7. Some of them say 6. That's 6, 7, or 800 degrees is where they switch. So this is a little bit small for our needs today. Now, so what we're going to do, we're going to be going to the 1/4-inch tip, and this is a 700 degree tip. I'll put that in there. Screw the little cover back on and resume heating. Okay, so temperature controlled irons, very important, very nice to have. The wattage is surprisingly high. When you need wattage from an iron, it's nice for it to be able to turn on and give you a lot of watts when you need it, and then come up to temperature and stop. As opposed to a gun, a lot of people think the guns are very powerful because they're big and they're heavy, and they're not. You know, they some of them are up, I mean, I've seen them as high as 125 watts, but this iron is 80 watts, and 80 watts to that little tip, very effective. And most irons that are not temperature controlled are 15, 25 watts. So yes, they'll come up to temperature, and they self-regulate by just in terms of how much heat they lose at a certain point, and they reach an equilibrium. But usually it's well over the temperature you want. It's too hot when resting, and then when you go to use it, it loses all of that reserve heat, all that residual heat that it's stored up in its mass, and now it's 25 watts is just not enough to get the job done. So yeah, temperature controlled irons. Keep your iron clean. A little ammonia helps. This is 10% ammonia and water. I'm going to put that on my sponge. Does a very nice job of keeping the tip clean. It's not corrosive, abrasive. Clean and tin. Always leave your tip tinned and you know, dripping with oxidizing lead. Wonderful environmental contaminants. Wash your hands after handling solder, obviously. Now we're going to get rid of some of this solder here, and I'll just pick this up for a moment and just get a good look at that solder, and tell me what you think. Not too bad. It's a little messy. This was previously repaired by a buddy of mine, and he neglected to make any changes to the bias following the repair. Huh, I got caught in there. So for whatever reason, he turned it on and it promptly blew up again. And we don't know whether there's a problem with parasitics, whether the bias was just too high, the transistor, the device gains were higher than they should have been, whatever. But we have a new box of devices here. We're going to melt and just lift these tabs. I will eventually remove the solder with a solder sucker. I happen to like solder suckers. You can use mechanical ones like this. No batteries required. They've always worked well for me. They do require a little bit of a technique. You can use electric ones with, you know, vacuum devices and what have you, but whatever you like. I do not advocate the use of solder wick. I do occasionally use it. There are instances where it is difficult to get that last little bit of solder out of some place, and the solder wick actually does a good job. But solder wick requires quite a bit of heat. I don't like to soak the circuit boards with heat if I can avoid it. I will melt the solder and quickly get the solder pulled in there and remove what I can. If I have to go back for another grab, I'll go back for another grab without achieving very high heats. And the other problem I've had with the solder wick on occasion is that it will solder itself to the board, and you can, if you're not careful, just pull traces right off the board with it. You know, you got to remove it and you give a little tug and the trace is gone because you've added so much heat. So we're not going to do that. Alright, my my soldering iron is blinking, meaning it's up to temperature. I put a little pilot light on mine. And so when the pilot light blinks out, I know that it's up to temperature. So let's do this. Now, I'm going for the ground first, because that's going to require the most heat. Okay. Now I'm using a thin dissecting probe, and I'm doing that deliberately because of its lack of strength. I don't want to put a lot of force into this. So that looks pretty clean. I'll get a little more out of that later. I'm going to do the same thing on this side. We're going to use the handy dandy digital meter to see what's going on here. And so I actually suspect this device is good. So now I have to go a little further. I have to confirm that. And the way I'm going to confirm that is I'm going to put a bias voltage on the gate. Not much, just a little. I get my bias source out here. Turn on my power supply. And move my coffee. So here's my supply. Going to put the negative lead on the gate, positive lead on the source. So VGS. We're going to look at our source to drain resistance, and it is indeed fairly low. And we're going to give it a little bit of bias. And it appears like that's working. So I'm in the megohms now. I'm going to reverse that. I'm going to make it a positive bias. So at about probably 2.5, 3 volts of positive voltage, my channel becomes very conductive. And here's where my digital meter completely fails. There's something going on here that it's not able to stabilize on the value. Yeah, it's toggling high and low. It's searching for a value. So there's some little bit of variability in there, maybe a little noise in my supply, my bias voltage. It's being amplified. But for all intents and purposes, I have to say that this device probably works. So I'm going to assume that device is good. Now, I'm also going to compare that with the original device, just basic DC measurements, just to see if they read the same. But I believe that this device is just fine. I have no reason not to believe that. So let's get back into this and get these other devices out. Now I am going to test these. These devices do occasionally fail. And if that were to be the case, we certainly could get the generation of parasitics. It's predominantly what they are used to do is suppress higher frequencies. If harmonics are present, they can sustain a fair amount of current over a long period of time. And they will heat up. The original devices in this failed due to not parasitics or other device failure, but overheat. A piece of rubber, don't know where it came from, what it was used for, but a chunk of rubber, I am told, was found to be stuck in the fan. And there was no thermal safeties to shut down the unit. And I am in fact pretty comfortable assuming that one or both of these devices will be bad. Well, now we've got the other parts out. We've actually removed the board, checked underneath, made sure there wasn't any little bits of solder floating around in there. Nice and clean, put it all back together, and it's time to move on to the next part. This wasn't too bad, but if you thought I added a lot of junk here and babbled on, the next part's really going to kill you. It's all schematics and service manuals, and we're going to go through this in great detail. We're really going to get into the weeds here. We're going to talk about the schematics, the drawings, the service manuals, information that's lacking. And if you really want to know how to be a tech that can go just a little bit beyond what the service manual provides you, you know, I hope you find this interesting. If you're not into the details, it's going to get really dull and mundane, and you might just want to skip to part 3 where we just put the parts back in. But you won't know. You won't necessarily understand how we're able to put the parts back in and make the adjustments required without blowing it up, unless you see part B. So here's part B. Thanks for watching, as always.